In this video, we're going to focus on some special cases of factoring and solving quadratics. The first special case we'll look at are perfect square trinomials. You'll notice these especially by looking at whether the first and last terms in the trinomial are perfect squares, meaning that you can take the square root and get an even number or letter. And in this case, the square root of x squared is x, and the square root of 9 is 3. What happens is you have a perfect square trinomial if half the middle term squared gives you the product of the first and last square roots. So half of -6 is -3. If I square that, I get 9, or 9x squared, which is the product of 9 times x squared. Half of 20 is +10. If I square that, I get 100. Well, the square root of this is 5, and the square root of that is 2x, and 2x times 5 is 10x squared. And so that's where this comes from. Let's take a look at how we can factor these quickly and easily just by looking at the pattern. So when you look at these, of course, you can always do the box or pants or guessing and checking. But what happens when you do this is -3 times -3 is +9, and -3 plus -3 is -6. And so you end up with this pattern where you get x minus 3 in this case, once you've done the box or the pants, equal to 0. The fact is that when you have a set of parentheses being repeated, the short way of writing it would just be one of those parentheses squared, equal to 0. And so perfect square trinomials can be written this way, and we find that this particular special pattern gets used very much, particularly in completing the square, which we do more with the honors class, but it's important for everyone to be able to use. Then when you solve this, it turns out that we get the same answer when we make our little mini equations. And so you just get x minus 3 equals 0, or x is equal to 3. We call this a multiplicity of 2 because the answer appears twice, the same answer. And when we graph, you'll see that that becomes important, but you don't have to know that word right now. In this other perfect square trinomial, you might have to take a little longer the first few times to recognize that your box or your pants result in the square root of the first term, 2x, the square root of the last term, 5, and since this is all plus, this will be plus, and we'll have this quantity happen twice, 2x plus 5 times 2x plus 5. And that's the special pattern. If you multiply these, 2x times 5, and double it, so you get 10x, you double it, that's 20x. It should give you this middle term. If it doesn't, you've done something wrong, or it's not a perfect square trinomial, which is possible. Since we know we'll get this answer twice, we only have to set up one mini equation here, and when we minus 5 from both sides and then divide by 2, we get x equals -5/2. So these are perfect square trinomials. Remember, you can always use the box or pants or even guess and check to do the factoring and then set up your equations to solve. The next special pattern is the difference of two squares. And you'll notice in this case, you only see two terms. What's occurring is that the middle term, the bx piece of the standard form equation, is missing. When that happens, it means that it's canceled when you factored it. So that tells us that this is a result of a plus-minus pattern in our factoring. Remember that if we have exactly the same thing in the two sets of parentheses, but one is plus and one is minus, the result is that those middle terms cancel. Well, since there is no middle term here, we can skip right to the parentheses. The first position is the square root of the first term, which is 2x in this case. The second position in the parentheses is the square root of the last term, which is 7 in this case. And because there's no middle term, and this is the difference of two perfect squares, one of these is plus and one of these is minus. Now be very careful. You cannot factor the sum. If this was plus, you'd have to leave this problem alone. We have our two factors. We take each one, we set it equal to 0, and we can solve to find our solutions. Our solutions are x equals 7/2 and x equals negative 7/2. Go ahead, pause the video, and try this one on your own. One word of warning. There is a GCF here that you should factor out first before you look to do the difference of two squares pattern. So, how'd you do? Notice that there's a 2 in common here. I factor out the 2 and I'm left with 9x squared minus 100. This is the difference of two perfect squares. I keep the 2 as my GCF, but my two perfect squares are 3x and 10, and then 1 minus and 1 plus. Doesn't matter if you put the plus first and the minus second. Notice that that 2 had no effect on my solutions. The only time your GCF will affect your solutions is if there's an x with it. And if that was the case, there would be another solution where this would be set equal to 0. Okay, sorry about the bells. I'm trying to catch them. Let's look at the final, for the regular class at least, the final pattern that you need to know. These formulas would be given to you. This is for the sum of two cubes and the difference of two cubes. Cubes being perfect cubes, meaning you could take the cubed root of them and get an exact number. If you don't know how to use other roots in your calculator, the third root, which is the cubed root, or the fourth root, or the fifth root, then you need to ask that question in class, and you might make yourself a note. In this first case, we look and we see that we have the sum of two perfect cubes, and you can verify that by doing the cubed root of 8 in your calculator and seeing that it's 2. And when you do the cubed root of 27 in the calculator, you'll see that the answer is 3. And so all you have to do is plug in here. Now I hate that these formulas use x and y because we have to be careful. I like a's and b's better so we can look at what a is and what b is. In the first case, your first set of parentheses is just the cubed root of each added together. So the cubed root of 8x to the third is 2x, and the cubed root of 27 is 3, and all we do is add those. So that gives us a good idea of what goes in the x position, the 2x in this case, and what goes in the y position, the 3 in this case. We're squaring that first piece, so when we square 2x, we square the 2, which is 4, and we square the x, which is x squared. Then we subtract, and here we're multiplying the x times the y. So you're multiplying 2x times 3. That's 6x. And then at the end, you take the second piece and you square it. Y was 3, so we're going to square that and put plus 9. So this is, if you think of these as A's and B's, it might be easier. This is a plus b, a squared minus ab plus b squared. You can do the same thing so that you don't mix up this x with that x. Take a minute and just try the second one. I know that plugging these in can get a little confusing, but pause the video and give it a shot now. So how'd you do? Again, it might be helpful to think of these as a's and b's. So we're using the cubed root of this and the cubed root of this to plug in. We have a 4x and we have a 1, and we do the exact patterns that you see in the formula there. So when we square x, what we're squaring is this 4x, which is where 16x squared comes from. And then we have x times y, which is 4x times 1, which is just 4x. We're using the plus just because it tells us to. And y squared means 1 squared, which is 1, of course. So again, these take a little practice to apply, but you would be provided with these formulas if I expect you to use them. You just have to know how to use them. The next 2 slides are for my honors class, so if you're in the regular class, you should fast forward to the summary screen now. For my honors students, it is possible to use irrational numbers to factor. If we're looking at the difference of what would be perfect squares if this piece was a perfect square, think about what you could multiply to get 7. Isn't it true that we took the square root of each of these? So what if we just used that fact and took the square root of it? We know that the difference of perfect squares will give us that plus minus pattern equal to 0. So you can factor this by saying x plus the square root of 7 and x minus the square root of 7. Try it. Multiply this back out. You'll see you have to get the middle terms canceling, and then square root of 7 times square root of 7, or negative square root of 7, is negative 7. So it works. And there is sometimes the need for this, so I want to make sure that you know that you can utilize that pattern. Again, we'll set each factor equal to 0 and solve. Try the second one here on your own and pause the video and then come back and check your work. So while you paused, I factored, but I also solved these equations so that you can see how to express your answer for these. You should pause again and make note of this and make sure that you jot down any questions you have about how to express your solution. The last special pattern uses imaginary numbers so that we can not just factor the difference of perfect squares, but the sum of perfect squares. And the way we do that is using I, because again, we have no middle term. So in a perfect scenario, if this was minus, you would have x minus 4, x plus 4. The problem is I need this to turn to plus 16. And so I can use 4i in place of that to account for that. You know that the middle terms will cancel, and when you multiply 4i times negative 4i, you get negative 16i squared. But I squared is negative 1, which means you really get plus 16. Go ahead and try the other one on your own. Solve both of them and pause the video. When you come back, you'll be able to see whether you were right. Okay, check your work. Jot down any questions that you have, and we'll address them together in class. Remember that these special cases can help you solve problems more quickly because they use common patterns that you can memorize. When solving, you can always default to the quadratic formula in every case. Don't forget to check your answers. If you're finding x, if you plug that value back into the original equation, you should make a true statement. If you don't, you've done something wrong.